Hello and welcome back. So last time we discussed the confusion matrix, right? And we calculated different types of metrics on top of that. What is sensitivity, which is the same as true positive rate, and what is specificity and what is positive predictive value. In this part of the lecture, we are going to build on top of these concepts to define what is meant by a receiver operating characteristic curve for a classifier. So, but to get there, we are going to first try to understand the role of threshold for a given classifier. Remember, we've discussed this in a previous video. For a given classifier, we can think, let's say if you've got a classifier x, right, f of x, then it essentially generates a real value to a float value, which we call the score of that example from that classifier. And then we can go ahead and binarize that score to generate a prediction label. So let's say if f of x is greater than that particular threshold, I'm going to call that threshold t. Then we're going to say that the prediction label for x is going to be +1, otherwise it is going to be -1. Typically, this threshold is set to 0 in support vector machines or in perceptrons. Everything above the line is going to be classified as positive, and everything below the line is going to be classified as negative. However, consider two lines in a machine learning setting, and both of them produce this. So let's say we've got a dead set. Let me make a drawing here. So let's say got two examples, two classifiers that solve the same classification problem. I'm going to use two different colors to draw those two different lines. Let me use the blue line over here that separates these two, right? So that's the straight line, assume that please. And then we've got, let's say, a differently colored line. Let's pick orange, okay? And that particular line, right? So we can say that if we use a very strict definition of classification, then the orange line has misclassified this particular point. Let me pick another color so we don't confuse colors here. Okay, so let's say we've got this example over here is being misclassified by this purple line, right? But if you think about it, the score that is going to be generated for this example is going by this orange line is going to be smaller than the score that the same line would generate for these four examples, which are positive examples and they are above the line, right? So if I move this line to this side, it's going to classify correctly. And if I compare its prediction performance to this blue line, after that move, they are going to come out equal, right? So in this case, our choice of the threshold is impacting our accuracy calculations. At a certain value of threshold, let's say a threshold of 0, the orange line that we have drawn will have higher errors or lower accuracies in comparison to the blue line. But that doesn't really affect the prediction scores that we are generating. So a simple translation of that line is going to change the definition of accuracy, and both of them are going to get the same value of accuracy. So we don't want to miss out on a good classifier just because its threshold choice is not optimal. So that's the essence of what we are going to do next. We want a classifier, or we want to evaluate the performance of a classifier irrespective of the threshold that we use to binarize those labels. It's a concept that some people who are especially beginning in machine learning have a hard time grasping. But if you think about it, you don't want a classifier which is otherwise as good as another classifier to be thrown out the window just because it's not tuned to the right threshold to binarize the labels. So in this particular example that I've given you, the orange line that we have over there is as good as a classifier at another value of threshold as the blue classifier is at this particular value of threshold, right? So both of them are going to be good classifiers. They're going to give 0% error for this particular classification problem if I define the threshold differently. I hope that that explanation helps or motivates you to or gives you an idea of why we are so much why we are so interested in this threshold value, right? However, one thing that we want to understand is what is the impact of this threshold. And let's say if I have a classifier and for that particular classifier, I set the threshold to t is equal to, let's say, infinity, a very large value, then no matter what the classifier produces at its output, the prediction label is always going to be negative. So if the classifier does not generate any positive predictions, that means it's not going to produce any true positives, right? I hope you understand that concept. And if you want to wrap your head around, you can, I welcome you to pause the video and think about what happens when you set the threshold to a very high value. Will that classifier generate any positive predictions? And the answer should be no, because if because of the way we have defined how we discretize these labels. On the other hand, if I use the threshold of minus infinity, then everything that is given to the classifier is going to be above, the score is going to be above minus infinity, and that example is going to be classified as a positive example. So you can think, or you can, I hope you can understand now that the choice of the threshold impacts the number of positive predictions that the classifier is generated, right? And what we want to understand is what will be the behavior of the true positive rate, or in other words, what is the role of how is the true positive rate or sensitivity or recall, all of these are the same thing. We've talked about that, right? How is that going to change as we change the threshold, right? So let's say if we make a conceptual plot in which we plot the threshold on the x-axis and we plot the true positive rate or sensitivity, which is defined as the number of predicted positive examples or true positive examples out of the total number of positive examples, right? So it's going to be TP by P. So that is the true positive rate. How does that change as we increase the value of threshold? And I've told you that when the threshold is infinity, the number of positive predictions is going to be zero. Therefore, the number of true positive predictions is also going to be zero. That means at t is equal to infinity, let's say at this value, whatever that is, at infinity, the value of the true positive rate, which is plotted along the y-axis, is going to be zero. Now, what happens when we have a threshold value of minus infinity? If we choose that value, then everything is going to be classified as positive. That means all the examples that are actually positive, those are also going to be classified as positive examples, right? So the true positive rate of that particular classifier or of any classifier at a threshold value of minus infinity is going to be 1, right? So it's going to be, the ratio is going to be 1. Whereas at t is equal to infinity, it's going to be 0. Now the interesting bit is, and first of all, I welcome you to pause the video and understand why the value of TPR is going to be 1 when the threshold is minus infinity, and why it's going to be 0 when it is when it is infinity, when the threshold is infinity. And once you are done with that, I want welcome you to understand, can the true positive rate of a classifier decrease with increase in threshold? So if we are increasing the threshold, let's say if we're going from minus infinity to plus infinity, can the TPR, the true positive rate of a classifier, increase, or can it decrease? Uh, so the question is, will this curve go down? Will it be, or can it go up? Okay, so that's the type of question. So you can pause the video and think about it. And as we know that when we increase the threshold value, the number of positives that are going to be generated is going to go down. That means either the true positive rate is going to stay the same, or it's going to decrease. So this curve is going to be a monotonically non-decreasing curve, right? Sorry, a non-increasing curve. So it's not going to increase at any point. And I welcome you to pause the video and try to understand the behavior of this curve for any classifier. If you've got a classifier and you choose a very high value of the threshold in your binarization, then the number of true positives is going to be zero. Okay, and if the value of threshold that you choose for your binarization is minus infinity, then everything is going to be classified as positive, so the true positive rate is going to be 1. However, in between these two, what I've said is that the the true positive rate of any classifier is not going to increase. Either it's going to stay the same or it's going to be decreased or it's going to decrease. So TPR is going to be what we say TPR versus threshold is going to be a tonically non-increasing function. Okay, and you can wrap your head around that by understanding how this true positive number of true positives change when we change the threshold. Okay, so that's shown over here in this curve, which is the same drawing, but it's probably a better way of showing the same thing. If you got your threshold on the x-axis, if you choose a very high value of your threshold, your TPR is going to be 0, and your TPR is going to be 100%, or it's equal to 1 when you have a threshold equal to minus infinity. And I welcome you to understand why the false positive rate so is going to behave like this as well. So the false positive rate of a classifier at a given value of threshold is the number of how many false positives it generates divided by the total number of negative examples. Okay, so if you go back to uh, this matrix that we have over here, we can see the definition of false positive rate is the number of false positives divided by total number of negatives, the number of total number of negatives that are given to us in the test set. Okay, so this is a definition of the false positive rate, and based on this definition, we can apply the same logic that we have used in defining how or in understanding how the true positive rate changes when we change the threshold. If you set a very large value of threshold, then the number of positives is going to be 0. So the number of false positives is also going to be 0. So this is going to be 0 divided by n, and the false positive rate is going to be 0 as well, right? When we have the threshold equal to a very low value for the classifier, then the number of false positives is going to be very large because everything is being classified as positives. That means, as a matter of fact, all negative examples are going to be classified as positives, right? Which is wrong, horrible. But what that means is that the false positive rate is going to be 100% because at that point, FP, the number of false positives, is going to be equal to the number of negatives because all negative examples at a threshold value of minus infinity are going to be classified as positives. So we get this point over here, which is shown over here in red. So let me please use the red color. So you can see that this point is where the false positive rate is going to be equal to 100%. And when the threshold is going to be infinity, positive infinity or very large value, then the false positive rate is going to be 0. Now it's interesting to analyze what happens in between these two threshold values, between plus infinity and these extreme values. As we increase the threshold, the number of false positives is going to go either going to stay the same or it's going to go down because the number of positive predictions goes down. That means false positive rate is also going to be a monotonically non increasing function of threshold. So the same thing goes here. The false positive rate over here is also going to either stay the same or it's going to decrease. So we can, if we plot the error rate, either in terms of the true positive rate, let me change a different color so people don't get confused. So let's say we've got error rate plotted on the y-axis, it can be either TPR or FPR. And if you've got threshold on the x-axis, then both of these curves, the TPR curve and the FPR curve, both of them are going to be monotonically non-decreasing. Okay, so they're going to behave like this. At a certain value of threshold, let's say if you pick this value of threshold, at that value of threshold, you're going to get a certain confusion matrix. you're going to get a certain number of false positives, a certain number of false negatives, a certain number of true positives, and a certain number of true negatives. And you can use those numbers to define a particular value of false positive rate and a particular value of true positive rate, right? So at this particular value of threshold, you get a certain value of FPR and you get a certain value of TPR, right? So those are the values at this point. However, if you change the threshold, accuracy is going to change. So because TP, TN, FP, and FN are going to change. The overall number of examples in the test set is, of course, is going to remain the same. But because the threshold has changed, therefore, the number of true positives, true negatives, false positives, and false negatives is going to change. So accuracy is going to change, and so will the true positive rate and the false positive rate. So at a different value of threshold, what we are going to see is that at that particular value of threshold, we are going to have a different value of false positive rate and a different value of true positive rate. Now, what we can do is the following. We can plot the false positive rate at a particular value of the threshold, which we know, against the true positive rate, and that is what gives rise to the to the receiver operating characteristic, or ROC curve, right? So ROC curve is a parametric curve that plots the true positive rate versus the false positive rate of a classifier at different values of thresholds. But the threshold parameter is taken out, right? And this is what we get. Okay, so we plot the false positive rate along the y-axis and the true positive rate along the y-axis. So for a particular value of the threshold of the classifier, we get a certain value of false positive rate and a certain value of true positive rate based on this error curve, right? And what this allows us to do is to express these two performance metrics, FPR and TPR, in the form of a curve. So each point that you see, this point, this point, this point, all of these points are FPRs and TPRs calculated for a given test set for the same classifier by changing the threshold value. Okay, and you get this curve at, and as you can see in the previous curve, when you had the threshold value set equal to infinity, both the FPR and TPR were equal to 0. So this point over here at this point corresponds to the threshold value, a very large threshold value, okay, at which both FPR and TPR are equal to 0. On the other hand, when your threshold value is very small or it is minus infinity, everything is going to be classified as a positive. Therefore, both your true positive rate and your false positive rate are going to be equal to 1. So this is this point. At this point, this corresponds to when the threshold was equal to this was when it was equal to minus infinity, and this is the point when the threshold is going to be plus infinity. And the other points actually come in between, and they give rise to this curve, right? Now, this is what is called a receiver operating characteristic. This is no S here. This is called the ROC curve for a given classifier. And what this allows us to measure is how accurate that classifier is at irrespective of its threshold. So what can be the true positive rate at a given false positive rate? And that's really important, and that gives us a wealth of information in a practical setting. So for example, if you're trying to design a machine learning model that is to be used for access control, okay? So let's say we've got a facial recognition system that recognizes a person's face before granting them access into a certain room or a bank vault. We want the classifier, or we want that machine learning model to have a very low false positive rate, right? So the operating threshold that we are, or the operating condition that we are going to pick for that particular classifier should conform to a value that corresponds to a very low false positive rate, right? Because we don't want anyone who is not authorized to enter that room to be able to enter that room, right? So we can use that particular value. Let's say if we allow that let's say 5%, at a false positive rate of 5%, we can calculate what is the true positive rate. and we can calculate how many times will the will the person who is authorized be restricted from entering that room. So that is what this curve allows us to analyze. So how does the false positive rate change? How does the true positive rate change as a function of the false positive rate? Ideally, we want a classifier that has a false positive rate of 0 and a true positive rate of 100. So we want a classifier for which the ROC curve looks like this. Okay, so that is what we want, right? And if you think about it a bit, then we say that the ideal curve, that the ROC curve that you have, is going to resemble something like this. If you plot the FPR on the x-axis and TPR on the y-axis, and let's say this is TPR equal to 1 and this is FPR equal to 1, then we want a classifier whose ROC curve looks like, uh, let me use this different color, that has an operating point over here, right? So they have a TPR of equal to 1 at a false positive rate of 0. So they don't produce any false positives, and while not missing, or they have 100% sensitivity, so they don't miss any, they don't classify anything that is actually positive as negative. So that should be the ROC curve for an ideal ROC curve, right? So this should be an ideal classifies ROC curve. And well, since we have discussed this earlier as well over here, if you have a classifier and you analyze or you plot its false positive rate and true positive rate across its threshold value, different threshold values, and both the false positive rate and the true positive rate are monotonically non-increasing functions of the threshold. And what that means is that the ROC curve that we get is going to be a monotonically non-decreasing curve. Okay, so think about why that would be the case. It's if you understand this bit, it should be relatively straightforward uh, for you to derive why this curve, this ROC curve, should always be monotonically non-decreasing. So an ROC curve is monotonically non-decreasing. Okay, what that means is that for an ideal classifier, the ROC curve should look like a square. So if this is 1, then this is 1, and the area under this curve is going to be, so it's a rectangle, right? So this is going to be 1, and this is 1. So 1 multiplied by 1 is the area under this curve, and that is going to be equal to 1. And the area under the ROC curve, AUROC as it is abbreviated, that can be used as the performance metric that is irrespective of the threshold of the classifier. So what that means is that if you want to get rid of the threshold and you want to analyze the performance of the classifier across all ranges of threshold, you can simply go ahead and calculate the AUC-ROC or area under the ROC curve. And the higher that number is, or the closer that number is, to 1, the better your classifier is. If it's equal to exactly 1, you've got yourself an ideal classifier. So just to summarize, what we've done so far is we've discussed how to determine the ROC curve. What we essentially do is we plot the false positive rate and the true positive rate of a given classifier uh, against its threshold value. So if we choose a particular threshold value for that classifier for a given test set, we calculate how many false positives it's generating and how many true positives it's generating, and we calculate the false positive rate and the true positive rate, and we plot this curve that is on your screen. I call it the false positive, like the threshold versus false positive rate versus true positive rate curve. Okay, or you can call it the error curve for a classifier versus threshold, right? So we can call it the error rate versus threshold curve. Okay, so for a given threshold value, it tells us what is the true positive rate and the false positive rate. Once we have done that, what we then do is we can plot the true positive rate versus the false positive rate by marginalizing or parameterizing out the threshold value, which gives rise to this ROC curve. And we've seen that the ideal ROC curve should be an ideal classifier should have a false positive rate of 0 and a true positive rate of 1. And because the ROC curve is a monotonically non-decreasing curve, therefore it should have an area under the curve equal to 1. So the AUC-ROC of an ideal curve is equal to 1 multiplied by 1 is equal to 1, right? And we can measure that, right? So this is the definition of ROC curve. At a very high level, it's a performance metric that tells us, irrespective of the threshold value, unlike accuracy, which is dependent upon the threshold, ROC curve tells us what is the expected true positive rate at a given false positive rate. And the area under this curve can be used as a single summary statistic that tells us how good or bad a certain classifier is. Now, before we move on to to more to a more detailed discussion about different properties of the ROC curve, I'm going to give you a certain example of how it's actually calculated. So let's say if you got 20 different examples in a test set, and we know what their true labels are. So we know whether let's say example number one is positive, and example number three, let's say it's negative. And for each of these the examples in our test set, we calculate the score that that particular classifier or a given classifier is generating. So let's say for a example number one, the prediction score that you get from a classifier is zero point 0.9, and we sort these scores whether it's in order of decreasing scores. So the most positive predicted example is going to be ranked number one, and then we got example number two, which has a score of zero point 0.8, and then 0.7, and so on. So what we've done here is that we've given the data set to the classifier, and we've given the test data set to the classifier, and we've calculated for each example how the prediction score. And that prediction score is then used to sort these examples. And once we have obtained that, then what we do is we choose a threshold value. Let's say if we choose a threshold value of 1.0 now, right? And at that particular threshold value, all of these examples are going to be predicted as negative, because all of these score values are going to be less than the threshold that I've chosen, which is equal to 1. So if I choose a threshold of 1, if 0.9 score, this example scoring 0.9 is scoring less than that particular chosen threshold. So it's going, when we binarize those labels, the prediction output is going to be negative. So this is going to be predicted as negative, and everything else is also going to be predicted as negative. With that, with those negative predictions for all of them, we can go ahead and calculate what the false positive rate is and what the true positive rate is. Because all examples at this particular value of threshold are being predicted as negative, therefore the false positive rate is going to be 0 and the true positive rate is also going to be 0. So that is what, in effect, we don't need infinity. What we need is just a value that is below the highest, that is above the highest scoring example in our given test set. And we can go ahead and calculate that. We can plot the false positive rate and true positive rate at this point. And then what we do is we change the threshold value to the next available score. So let's say we've got a score of 0.9. If I pick that score, then this example is going to be now classified as positive, whereas all the other examples are going to be classified as negative. And then I can go ahead and calculate the false positive rate and the true positive rate again, and I can add a single point in this curve. Okay, and this is how you actually go ahead and calculate. Then we increase the threshold value to 0.8, this one, and we can calculate how many true positives and false positives there are, and we keep on doing it until we've gone through all of the example scores, and this gives rise to this score, then this ROC curve, this receiver operating characteristic curve, right? So I've shown you the mechanics of how it's calculated, right? At a high level, what this curve is telling us is at a false positive rate of, let's say, zero point 0.2, the true positive rate of this classifier is 0.5. That means if I allow the classifier to generate 20% of false positive, that means uh, about out of all the negative examples, if I allow that 20% of those examples are classified as positive, then my classifier is able to detect 50% of all positive examples correctly. So that's the meaning of this particular point. And it's really important to understand, spend some time trying to understand this, because these curves are crucial in analysis of performance, and it's used uh, in selecting what classifier is optimal and how we can compare different classifiers. So I hope this definition, this explanation of how it's calculated is going to help you. And we also are going to have a lab session on this. Now, where does the word ROC come from? That's a pretty interesting story. So during the Second World War, people had developed radar and they wanted to analyze how good or bad a particular radar was, right? And the way a radar works is that it sends out a beam and which is reflected by an object that is flying out there. It can be a bird or it can be a plane, it can be Superman, whatever. And you get a reflection, right? And based on that reflection, you threshold that reflection or the strength of that reflection to separate out or to identify whether a particular target is out there or not. So what they did used to do is they flew a plane that they knew where it was at, and then they analyzed the reflections off of that plane to calibrate that radar. And they could measure the performance of a particular radar by simply plotting how many false positive detections it was generating. That means it was detecting an object when there was actually no object there versus the true positive rate of that classifier of that radar at a given threshold value, that is what cutoff to use, and then that gave them an idea of how good or bad a particular radar was. So to have a perfect radar, what we wanted to have is it's able to detect all the planes and none of the birds, right? So it's going to have a TPR of equal to 1 at a false positive rate of 0. That's where historically, as far as I've been able to explore, this is where the name of receiver, because there's a radar receiver, and that's where the name comes from. And because it analyzes how the performance of how the false positive rate and true positive rate for a given receiver change at different operating points, which are essentially thresholds. So it tells us the receiver operating characteristic for a given radar, and that's where the origin of this curve is. Okay, so I want you to think about these questions that are on your screen right now in order to gain a better understanding of ROC curves. We've already talked about what would the ROC curve for a perfect classifier look like, but I want you to think about what will be the ROC curve of a random classifier. And the answer to this question is it's going to look like something like this. So the false positive rate is going to be exactly equal to the true positive rate. But I want you to understand why that would be the case. Okay, what will be the ROC curve for a classifier that always predicts the positive class? What is its ROC curve going to look like? And the answer to it is again the same thing as the random classifier. But I want you to think why that would be the case. What are the underlying assumptions of the ROC curve? And that's really important. We saw that accuracy had a certain set of assumptions. It assumes that the data set accuracy assumes that the data set is balanced, and the misclassification of a positive example into a negative example or a negative example into a positive example, it's pretty much the same. And then we had the case in which we talked about that accuracy is dependent upon the threshold that you select. Now we know that the ROC curve is independent of the threshold because it analyzes the performance of a given classifier across all values of the threshold, right? So that assumption is gone. But are the other two assumptions still there or not? Think about it. The answer is yes, but to both of them. But why is that the case? Okay, so that's the case. That's the part I want you to think about, and then I also want you to think about what part of the ROC curve is the most important. So if you plot the ROC curve for a given classifier, and the false positive rate is on the x-axis, of course, and then the true positive rate is on the y-axis, and you've got a curve like this that goes like, let's say this is 1.0 and this is 1.0. Then what part of the ROC curve is the most important? Is it this part? Is it this part? And what does that actually mean? I'm going to help you understand that a bit in a bit more detail. It depends upon the application. So for a given application, ideally, we all know that the false positive rate should be zero with a true positive rate of 1.0. But that's not always going to be the case. So in certain settings, we want very few false positives with a very high number of true positives, or we want a very small false positive rate and with a very high true positive rate. But I want you to think of scenarios in which we really want a very low false positive rate and a very high true positive rate. And a hint for that is it relates to the uh, number of or the class imbalance ratio. If the number is much smaller than the number of negative examples, then this region, this initial rise of the classifier, that means the value of the true positive rate at very small values of false positive rates is going to be much more important. But why? That's what I want you to think about. Okay. And we've already talked about that the area under the ROC curve, the ideal of an ideal ROC curve is going to be 1, and that we can use as a metric, right? So we've already talked about it. There's another performance metric that you can derive from an ROC curve, and that is called an equal error rate. So at that point, in this case, that's the point where the false positive rate over here, okay, and so this is the false positive rate, becomes equal to 1 minus the true positive rate. So that's the point that is called as the equal error rate for a given classifier. So it's generating equal number of type 1 and type 2 errors in percentages at least at this particular point. Okay. Now, some practical questions. Out of these two classifiers, which of the two classifiers do you think is performing better? The ROC curve for classifier C1 is shown as a solid line, and then the classifier C2 shows the ROC curve for that is shown as the dotted line. The area under both of these, AUC-ROC, for both of these is exactly the same. But which of the two classifiers do you think is better, and under what conditions? So think about that, and if you have any questions, you're always welcome to post that. There's another term that some people use. It's called AUC-ROC-N or AUC-ROC, let's say 0.1, and that is the area of the ROC curve at a given threshold of the false positive rate. So if we say that we want to calculate the AUC-ROC, the ROC curve, when the false positive rate is less than 10%, then what we are interested in is essentially this area over here, and we can calculate that. It's typically used in applications where we are interested in generating a ranking of examples. Let's say we've got a bunch of proteins, and we want to identify which of them are actually involved in, let's say, promoting the coronavirus. We can have thousands of proteins, but what we want to do is we want to sort them according to their predicted ability to engage the coronavirus, for example. And we can only test, let's say, 10% of them. Then we want to evaluate what is the expected number for that machine learning model that we have developed to do that, to do this sort of sorting. What's the expected percentage, what's the expected number of true positives in that case? Another way of thinking of it is, like, if we have 1,000 movies, uh, and I can only watch, let's say, 10% of those movies, then let's say if you want to evaluate the performance of a recommendation system, let's say Netflix, then out of those 10% of the movies, of all the movies that I have, what's the expected number that I'm going to like? So these curves can be used in a number of different scenarios. Okay, so we can also calculate the average of different ROC curves. Let's say if you've got multiple ROCs from different classifiers, you can take an average of them, and it's really straightforward to do. There are libraries available out there that allow you to average ROC curves. And similarly, if you have two different classifiers, you can take the convex hull. Or if you've got multiple classifiers, you can take the convex hull of those the ROC curves of those classifiers. So let's say if you got classifies A, B, C, and D, and each one of them produces different types of errors. Then you can construct a classifier that is a convex hull of all of these. So it essentially captures all of those, right? So that can be an optimal classifier by combining all of these classifiers. So these can be used for combining different types of classifiers. It's a bit advanced for the stage of the module where we are at right now. But once we are going to talk about ensemble methods, if you've got, let's say, different classifiers and we want to combine their outputs, then we can calculate what's the best expected performance we can get by combining these different types of classifiers. And that is typically done by constructing what is called the convex hull of these classifiers. Okay. And you can also calculate multi-class ROC curves if you've got two classes. We've already talked about those classifiers. We talked about how ROC curves can be used for that classification problem. But if you have a classification problem with more than one class or with more than two classes, let's say if you've got three classes, then what you can do is you can construct the ROC curve of one class as take that as positive and the other two as negative and construct one ROC curve. And you can calculate the area under that curve, and then you can do the same thing for the other two classes. Another way you can do it is to use, uh, you can calculate the ROC curve of classifier number of class number one versus class number two, or class number one versus class number three. And then you can do it for class number two versus class number three. And that is called the pairwise computation of ROC curves. So, so to summarize, we have talked about the ROC curves in pretty detail, how they are constructed. A classifier that scores examples. So if a classifier scores positive examples to be higher than negative examples, so if a classifier ranks positive examples higher than negative examples, its ROC curve is going to be perfect, no matter what the threshold I choose, because the positive examples are always being ranked higher than the negative examples. So we're going to get a pretty good ROC curve, an ideal ROC curve for that classifier. Okay, so I hope you are able to relate how ranking of classification examples or test examples in a given test set by a classifier is related to the ROC curve. Okay, so for people who are interested in statistics, ROC curves are related to something called rank tests. Okay, so you can welcome to explore that on your own, but that's for people who are interested in how different type of rank tests relate to ROC. ROC is actually a rank test. For others, for if you just want to use it for classification, I'm going to talk about what libraries you can use to compute these ROC curves in a later video. Okay, but what they allow us to do is to measure the performance of a classifier irrespective of its threshold, right? So if you've got two different classifiers and we want to analyze the performance of those classifiers, we can construct the classifiers or the ROC curves for those classifiers, and we can calculate the area under those, and we can say we can think of we can use that to identify which of the two classifiers or which of the two features, for example, is better than the other. Okay, thank you.